Hello folks, this is Jack again with another video presentation. This time it's on digital systems, which include JK flip-flops as the sequential part and combinational logic. Okay, again this is primarily for digital electronics UG2. It's not an introductory presentation at all. It's more of a revision stroke summary stroke consolidation. Okay, this is the actual circuit in question. We can clearly see that there's a sequential element as well as a combinational element. There's two JK flip-flops and two AND gates and one OR gate. Right. Now, just like in combinational logic, we can actually derive a circuit and a truth table from the Boolean expression. We can actually do the same for sequential logic. So I'm just going to show you how to do that. Sequential logic and combinational logic are there. A typical digital system will include sequential and combinational logic, so this is really a real digital system here. Now the aim of this session is to determine the following for the digital system shown in the previous slide. The Boolean expressions for J1, K1, J2, K2 and the final output F. The Boolean expression for Q1 next and Q2 next using the Boolean expression obtained in part 1. The state transition table using the Boolean expression in part B. Now, on the face of it, this may seem a difficult question, but let me assure you that once we actually go through it step by step, you'll find it quite straightforward. Right. The Boolean expression for J1, well, that's simply there's a combination logic gate there just before J1. That's an AND gate. So J1 equals A and Q2. Would you agree? K1 equals simply Q2. J2 equals Q1 bar. K2 equals Q1 or B. F equals Q1 and Q2. The general Boolean expression for Q1 next can be determined from the characteristic table for JK flip-flop. This is nothing more than a simplified minterm for Q1 next. The simplification can either be achieved using Boolean algebra techniques or Karnaugh maps. Let me just show you what I mean. Now this actual part here has got nothing to do with the circuit previously. This is just looking at the characteristic table of a JK flip-flops, and that is the characteristic table of a JK flip-flop. Now what we're going to do now is identify the Q1 next outputs for when they're 1. In other words, do you remember what we did with the minterms? Well, we looked at the output F, and every time F was high, we call that a minterm. Well, this is the same thing, but this time we're relating it to, we're targeting Q1 next, indicated by Q plus. Now it's high 4 times. If you write down the minterms for every time it's high, they are these. Would you agree? Now simplify those. If I'm looking at this now from the left to right, term 1 at the left, 2, 3, 4, 4 at the right. Now terms 2 and 4 have got something in common, would you agree? J and Q bar. So they can be J and Q bar. Terms 1 and 3 have got something in common, K bar and Q. So Q1 next simplified equals J and Q bar plus K bar and Q. Alternative method, Karnaugh map. Of course it's going to end up with the same thing. There we go. Okay. Now that we've got this kind of generic Boolean expression for Q1 next, all we have to do, well, I'll show you, it's quite simple. What we do is, that's a generic expression for Q1 next. What we can do is just have 2 of those generic equations, make it specific to our circuit. Because there's 2 flip-flops, we're going to have 2 Q1 next. 2 Q next. One's going to be Q1 next, and substitute your Boolean expressions obtained for J1, K1 into this generic expression to make it more specific. Do the same with Q2 next, J2 and K2. That is it. Now these are the Boolean expressions for Q1 next and Q2 next for that circuit, the first circuit that we've seen on the slides. Okay. Now 2 flip-flops, that means there's 2, sorry, I do apologize. 2 flip-flops means there's 4 unique states. However, there's also 2 external inputs, so every one of those states has to appear 4 times so it can fully exhaust all conditions of A and B. Okay, there we go. And just write down Q1 next according to the Boolean expression that we obtained previously. Write down Q2 next according to the Boolean expression that we obtained previously, and write F according to the Boolean expression that we obtained previously. Please take some time on this and check it through that it does make sense. But if you do work it through, it will make sense. Relate Q1 next to Q1, Q2, A, B, although B isn't relevant in Q1 next. But do spend a couple of minutes and fully make sure that you understand it totally. Okay. Now, what follows now, we've actually determined the state table from the Boolean expression. Would you agree? That's what we did. We determined the Boolean expressions from the schematic diagram of the digital system. From the Boolean expression, we obtained Q1 next, and Q1 next took 2 steps. First, there was a generic expression for Q next. Then we made it specific by substituting our expressions obtained from our digital system into the generic Q next to make Q1 next and Q2 next. From that, we determined the state table. Now what we're going to do is derive the state transition table. And this is nothing more than what inputs do you need for the JK flip-flops for those transitions to occur. Now we can look at the excitation table for a JK flip-flop, and it's almost a tedious task really of actually converting a state table to a state transition table, but we're going to have to do it. Whatever the transition is, that's what those inputs are needed. For example, if a transition needs to occur from 1 to 0, Q is 1, Q next is 0, then J has to be don't care, K has to be 1, and you're going to have to do this to all rows of Q. And here we go. This is the final thing. Okay, I'm going to be brief because I'm running out of time again for the YouTube 10-minute limit. But please do take some time. Have a look at every slide in detail, and if there are any questions, please raise them through normal channels. Okay, I'd like to thank you for listening, and I'll see you soon. Bye.